Alright, in this video I'm going to show you some test-style examples for derivatives involving trig functions. Starting with a tangent line problem. We're given a function, f of x equals 24 multiplied by 1 minus cosine of x, all raised to the power of 3. And we're asked to find the equation of the tangent line of this function at x equals pi over 2. So I'm going to get the basic building blocks of our tangent line. We're going to have y minus f of pi over 2 is equal to m times x minus pi over 2. And then we'll plug in the pieces. Y minus whatever that is equal to whatever the slope is times x minus pi over 2. So let's figure out these blocks. F of pi over 2 is 24 times 1 minus the cos of pi over 2, all cubed. What is the cos of pi over 2? What's the cos of 90 degrees? So you either memorize it or you think about this skinny triangle that's there. It's almost 90 degrees. What's happening to the adjacent of that triangle as we shrink that angle down, or increase that angle up, I guess, to 90 degrees, as the adjacent gets smaller and smaller and smaller. When it's exactly 90 degrees, the adjacent is going to be 0. Cosine is adjacent over hypotenuse, so 0 divided by hypotenuse, which is going to be 0. So cos of pi over 2 is 0. I recommend memorizing that instead of thinking about these pictures, but do what suits you. 24 times 1 cubed is 24 times 1, which is 24. So that's our y value. That's our y1. That's our number that we put there. Now we need m. We need the slope. We have a little bit more work for that one. M is equal to f prime evaluated at pi over 2. So we have to take the derivative. F of x is 24 w to the power of 3. I replaced everything in that bracket with the letter w. So w is equal to 1 minus the cosine of x. F prime of x is 3 times 24, which is 20 plus 4 times 3, so 60 plus 12, 72, w squared times w prime. So 72 times 1 minus the cos of pi over 2, all squared, multiplied by the derivative of 1 minus the cosine of x. Derivative of 1 is 0. Derivative of cosine of x is negative sine of x, so I have negative sine of x. Oh, I don't put the pi over 2 in yet. I'm getting ahead of myself. This is still x. We haven't evaluated it. We're going to evaluate it later. So 72, 1 minus cos of x all squared. Negative becomes positive sine of x. Now m is going to be f prime at pi over 2. So that'll be 72 times 1 minus 0. We already did that. Cos of pi over 2 is 0. And then what's the sine of pi over 2? Sine of pi over 2, think back to that skinny triangle. In that skinny triangle, the adjacent goes to 0, but the opposite goes to scrunch down, to squish down onto the hypotenuse. Sine is opposite over hypotenuse, so 5 over 5, 7 over 7, whatever it is, it's going to be 1. So sine pi over 2 is 1. We just get 72. So that's our slope m, that's our answer. So that's how you do that type. All right, another type. What type of derivative rule is this? This is a base that contains x and an exponent contains x. Base and exponent contain x. So we need to use logarithmic differentiation. I'm going to start by taking the ln of both sides. Ln of f of x is equal to ln of the other side. Ln of the tan, why did I put that? Ln of the tan of x to the power of secant of 2x. And then we can bring the power down using that rule for log functions. The secant of 2x comes down in front times the ln of the tan of x. And we'll take a derivative, keeping in mind that we have a product rule now. We have an a times a b on the right, like we almost always do when we're doing logarithmic differentiation. A is the secant of 2x. B is the ln of the tan of x. When we take the derivative of the secant of 2x, we can replace the 2x with a w. So a prime is going to be secant w tan w. That's one of our special rules for the derivative of the secant. And we multiply by a w prime. And then I'll substitute in what w is. W is 2x. So secant 2x tan 2x times 2, the derivative of 2 times x. I'll put that out front. 2 secant 2x tan 2x. So that's our a prime. Now b, when we find b prime, since this is the ln of w, we're going to have w prime divided by w. So the derivative of tan of x, which is secant squared of x, divided by tan of x. Don't do weird stuff. Leave it alone. Don't look for simplifications. Even if they're there, don't bother. Okay, now we're going to plug those in. We'll plug those in when we take the derivative of both sides. On the left-hand side, we have f prime over f. On the right-hand side, we have a product rule. AB prime plus BA prime. So A is secant of 2x times B prime. B prime is secant squared of x over tan of x. Plus b times a prime, so plus the ln of the tan of x multiplied by the giant expression we got for b prime, 2 secant 2x tan 2x. We're almost at the end of this thing, this monstrosity of a question. I'm going to cross multiply by f of x, and we're going to replace f of x by what its original function is, just to save some writing time. Tan of x to the power of secant 2x times all that business that got put there. Secant 2x times secant squared x divided by tan of x plus 2 secant 2x tan 2x times the ln of the tan of x. And is anything missing? Hopefully not. So one step I skip that I usually write is the cross multiplication step, showing multiplication by f of x, and then doing the last step, replacing f of x by what its original function is at the very top. I did it all at once just because the expression there is so beastly I did not want to write it again. It's not very nice. All right, let's go weirder. That wasn't weird enough. Let's pick it up a notch and go to the question types involving data. Here we have a function h of x, which is defined as f evaluated at 2 times the sine of x. And we're told some information about what f of x is at different x values. What is f of 0, f of 2, and so on. We want to find the equation of the tangent line at x equals pi. So let's do the easy part, the part that doesn't require any calculus. What is the equation of a line? So y minus the y value, so y minus h at pi equals m times x minus pi. So that's our equation of the line. Now let's make it a tangent line. Let's get h of pi. H of x is equal to f of 2 times the sine of x. So h of pi is going to be f of 2 times the sine of pi. The sine of pi is 0. So if pi is 180 degrees, imagine drawing that little triangle there, but scrunching it down so that the opposite side goes all the way to 0, because that's what the triangle looks like at 180 degrees. Your opposite 0, tan, or sine is opposite of hypotenuse, so you have 0 divided by whatever the hypotenuse is, 0 over 7, 0 over 2, whatever it is at 0. So sine of pi is 0. 2 times 0 is 0, so we have f of 0. And then from our table, f of 0 is equal to 3. So I use that data right there. So we can plug that in. Y minus 3. Something times x minus pi. Now we need to find the m. M is h prime evaluated at pi. So h of x is f of 2 sine of x. I'm going to rewrite that as f of w. And we have to use our general form of the chain rule. H prime of x is f prime of w times w prime. All of our chain rules look like this. Derivative of e to the w is e to the w times w prime, because the derivative of e to the x is e to the x. The derivative of ln of w is w prime over w, which can be rewritten as 1 over w times w prime, because the derivative of ln of x is 1 over x. The derivative of sine of w is cos of w times w prime, because the derivative of sine of x is cosine of x. So all of those chain rules follow this general formula. Now let's put the function back in. So this is f prime of 2 sine of x multiplied by the derivative of 2 sine of x, which is 2 times the cosine of x. Now we can evaluate it at 0, or pi rather, h prime of pi. So we'll have f prime of 2 times the sine of pi times 2 times the cosine of pi. Well, we already found that the sine of pi is 0, so we have f prime of 0. And cos of pi, so going back to that picture on the top right, pi is 180 degrees. What happens to the adjacent? When that angle gets scrunched down? Well, when that angle gets scrunched down to pi, the adjacent is equal to the hypotenuse. However, we are in the negative x direction. So the adjacent has become negative of whatever the hypotenuse is. So let's say the hypotenuse is 5. At 180 degrees, the adjacent is negative 5. When you divide them, because cos is adjacent over hypotenuse, you get negative 5 over 5, which is negative 1. So cosine pi negative 1 is worth memorizing. Okay, now from our table, what is f prime of 0? Okay, you can use green. F prime of 0 is 10, so I'll put a 10 in. So we have 10 times negative 2, which is negative 20. And there's our answer. There's got to be a color I haven't used. What haven't I used yet? Light blue. I'll take it. That's our answer. Y minus 3 is equal to negative 20 times x minus pi. All right, what if we flip it around? What if instead of having this mystery function on the outside, what if we have the mystery function on the inside? So in this example, h of x is 3 root 2 times the sine of 3f of x. Now we're given similar looking data to the last problem. We want to find the equation of the tangent line at x equals 0. So let's do the easy part. Y minus h of 0 is equal to m times x minus 0, our x coordinate. All right, so let's do the first part. What's h of 0? H of x is 3 root 2 times the sine of 3f of x. H of 0 is 3 root 2 times the sine of 3 times f of 0. We have to pull some data from our table. F of 0 is pi over 12, so I'll pull that out. Three root 2 times the sine of 3 times pi over 12. That fraction can be reduced. 3 pi over 12 is pi over 4. 3 root 2 times the sine of pi over 4. We have to use one of our special triangles. Our pi over 4 triangle. And sine is opposite over hypotenuse, so we get 1 over root 2. So we have 3 times root 2 divided by root 2. The root 2's cancel, we just get a 3. Now we need to find m. H prime of 0. H prime of x. So I rewrite h of x actually. Rewrite it here so it's easier to reference. H of x is 3 root 2 times the sine of 3f of x, which is 3 root 2 times the sine of w. Keeping in mind that 3 is a constant and root 2 is a constant. So we have a constant times a function. It doesn't get involved in the derivative. H prime of x is going to be 3 root 2 times the cosine of w times w prime. That's our new chain rule. Okay, so let's plug in the pieces now. 3 root 2 cos of 3f of x multiplied by the derivative of 3f of x, which is 3 times f prime of x. It's the best we can do. We don't know what f of x is, so the derivative of f of x is f prime. Now we'll evaluate it to get m. So we'll have 3 root 2 times the cosine of 3 times f of 0 times 3 times f prime of 0. So f of 0, we're going to use that again, pi over 12. And now we need another piece of data. We need f prime of 0, which is 10. Three times pi over 12, so that's going to be pi over 4. And then we can simplify. Cos of pi over 4, we go up to that special triangle. Cos is adjacent over hypotenuse, so 1 over root 2. 3 root 2 times 1 over root 2. Times 30. Root 2's cancel. We get 3 times 30, which is 90. So our slope there is 90, and that's our answer. right, so we're not getting away from multivariable functions just because we got into this part. Here's a multivariable function involving sine and cosine, function of x and y. X times the cos of y plus y times, or not times, y to the power of 2 minus sine squared of x. So what we're going to do is we're going to think about what this looks like if we're taking a y derivative. For f sub y, we treat x as a constant. So what this looks like is f of y is equal to x times a constant plus y to the power of a constant. If x is a constant, sine squared x is a constant too. And so is 2 minus sine squared x. All that stuff is a big constant as far as the y derivative is concerned. If we take the derivative with respect to y, we'll get 1. Oh, never mind, not x times a constant. I screwed that up. It's constant times cos y. So when we take the derivative of constant times cos y, we'll get constant times negative sine y, plus, when we take the derivative of y to the power of a constant, the constant will come down, times y to the power of constant minus 1. So that's how you think about a derivative like this. When it gets complicated, when it gets messy, simplify. Make an analogy. I didn't even use a number for x. I just called it a constant. And then think about what you would do if that constant was a 7. How do you take the derivative of y to the 7? 7y to the 6. How do you take the derivative of a constant times any function? The constant times the derivative of that function. So we just use those rules extremely carefully. Now, so let's write this down, not with the word constant, but with what that constant is in each of these pieces. So we have x multiplied by negative sine of y plus that constant power comes down, so 2 minus sine squared of x multiplied by y to the power of 2 minus sine squared of x minus 1. Subtract 1 from that power. We can simplify that a little bit. We have a 2 and a negative 1. We can collect like terms. We'd also simplify, put the negative up front of the first term, so negative sine of y plus 2 minus sine squared of x times y to the power of 1 minus sine squared of x. And that would be your answer. Don't do weird stuff. Don't be a hero. Do not simplify. Under any circumstances, do not simplify like beyond putting the negative out front, putting the constant out front, changing the order of multiplication if you want to, but don't do stuff with trig identities. Do not use complicated trig identities. We're not teaching them, we don't want you to use them. All right, another one, another multivariable derivative problem. We have the x derivative of this nasty looking expression evaluated at 1, 0. So let's break it down. Let's think about what it means to take an x derivative of an expression like this. To take the x derivative means we treat y constant. Treat y as a constant for the x derivative. So I'm going to rewrite this as a function of x. F of x is equal to 4 over a constant multiplied by e to the power of constant times x plus 3 times the ln of constant, I gotta put that underneath, plus 3 times the ln of constant plus constant times x. Now how would we take the derivative of that? So the 4 over constant just stays, it doesn't participate. 4 over constant. And then we have e to the w times w prime for the derivative of e to the constant times x, plus 3 times ln of the derivative of ln of w, which is w prime over w. I'll call it u prime over u, since we already used w for the above part. So we're going to use that format for our derivative of this function here with respect to x. So we have 4 over tan y, that's our constant piece, since we're treating y as a constant, tan y is also a constant. And we have e to the w times w prime. So e to the negative 5 x sine y times the derivative of negative 5x sine y with respect to x, which is going to be negative 5 times the sine of y. And now the second part, we have 3 times w prime over w, or u prime over u, 3 times, so the derivative of constant, so let's say 7 plus x cos 7, so 0 plus the cos of y gets factored out front, cos of y times the derivative of x, so cos of y times 1, all divided by y plus x times cos y. And then we can simplify this slightly. I'm going to bring the negative 5 and the sine y out front. Ooh. I'm going to change the question too. My apologies. I didn't think this one through enough, did I? Let's see. I want something that will not cause us problems, because we're about to have problems. Let's go with pi over 4. Almost caused some trouble here. I don't want to cause trouble. All right, so I can bring the negative 5 out front. I have negative 20 sine of y over cosine over tan of y times e to the negative 5x times the sine of y plus 3 cos y over y plus x cos y. Now we'll evaluate this at, do I want to do anything else to this? Let's also change it more. I should have done the question before making the video, right? You'd think I would have done that, but I'm not doing that. I'm just going right at it. Okay, so the question is now completely changed. It's find f sub x at 0, pi over 4. It'll make some of these steps nicer. So f sub x at 0, pi over 4, we have to substitute the right thing in the right spot. So we have negative 20 times the sine of pi over 4 over the tan of pi over 4 times e to the negative 0, e to the 0. Placing x with 0, I have 5 times 0 times sine pi over 4, whatever that is, it's going to all multiply out to 0, plus 3 times the cos of pi over 4 divided by pi over 4 plus 0. And we can simplify. E to the 0 is 1. Sine of pi over 4 is 1 over root 2. Tan of pi over 4 is 1. So I'll put these facts down here. Sine pi over 4 equals 1 from our special triangle. Cos pi over 4 is equal to 1 from our special triangle. And tan of pi over... What am I doing? 1 over root 2. 1 over root 2. 1 over root 2. I'm getting excited about the last one. Tan pi over 4 is 1. So I'm going to plug all those in. E to the 0 is equal to 1. I'll put that there too. So there's our facts. And then we'll simplify. So we have negative 20 over root 2 plus 3 times 1 over root 2 over pi over 4, which does not simplify very nicely at all. Negative 20 over root 2 plus 12 over pi times root 2. This was too hard. In retrospect, from beginning to end, too hard. Sorry. I don't want to scare you. This would not be a test question. It's too difficult to put on a test. There's too many things to get wrong, and I probably have a mistake here. Let me know if I do. All right, getting into things that are not too hard. I hope. All right, can we marry trig functions to optimization? Absolutely. Will we solve a full-blown optimization question involving trig functions? Absolutely not. But we can solve pieces of one. This question is kind of a question in reverse. We've been given a Lagrange function. So this is on the multivariable optimization material. And this Lagrange function is a function of 3 variables, x, y, and lambda. It's given by x squared sine y plus e to the y minus lambda x plus lambda cos xy minus 2 lambda. And the question is, what is the constraint? So we have to know what the form of the Lagrange problem is. Lagrange function has the following form. F is equal to our objective function, little f, plus lambda times g. So little f is our objective. And g is our constraint. So judging from this, we can rewrite our expression f of x comma y comma lambda. I need some space. I gotta do it down here. F of x comma y comma lambda is equal to x squared sine y plus e to the y. So there's no lambda pieces in those. So they're not part of the constraint. The pieces with the lambda are part of the constraint. I'm going to common factor lambda out. So plus lambda times negative x plus cos of xy. Oh, close the bracket too early, minus 2. And our g is our constraint and has form g of x comma y is equal to 0. So we found our g. We found this. All we have to do is set it equal to 0. So we've got to look for that. Negative x plus cos of xy minus 2 is equal to 0. Negative x plus cos of xy minus 2 is equal to 0, and there we have it. So we do need to keep this, oh, purple highlighter. We need to keep this part in mind. That part is important. The constraint is equal to 0. It's not equal to lambda. And all the other stuff is kind of baloney. You can't get any of those with anything that means anything. The whole part of the exercise is, can you identify the constraint? And just mixing in the trig stuff because why not? Right? It doesn't really matter if there's exponentials, logs, trigs, polynomials. It's all the same thing. It's the structure. The part that's multiplied by lambda is the part that makes up the constraint. Factor out lambda and look for the part that has the constraint expression, the g of x comma y is equal to 0. Okay, last question, I think. Yeah, last question. Suppose we want to maximize the function y sine of x subject to this constraint ln of y plus sine of x plus y cos of x equals 1. Using the method of Lagrange multipliers, what system of equations must you solve to find the critical numbers of the Lagrange function? We will not find those critical numbers. It is too hard, but we can find the system of equations that we would need to solve. We would need to start by creating the Lagrange function. Capital F is equal to little f plus lambda times g. And actually we have to do one further step, or one step 0, often missed, is we need to put the constraint into standard form. Put constraint into standard form. This is also a multiple choice type question without the options, but we'll just pretend there's options there. We'll pick the right one. So our constraint put in standard form is the ln of y plus sine of x plus y times the cos of x minus 1 is equal to 0. We just have to bring everything to one side, so we can say that constraint equals 0. So I've done that. Our constraint is just all this stuff. G of x, that's our g of x comma y is all that stuff. Let's put it all together into our Lagrange function. So we have y times the sine of x plus lambda times the ln of y plus sine x plus lambda y cos of x minus lambda. So that's our capital F. Now we need to make our system of equations. Our system of equations comes from taking the three partial derivatives, the x, the y, and the lambda, and setting them all to 0. F sub x is equal to y times the cosine of x plus lambda times w sub x over w plus lambda y times the derivative of cosine of x, which is negative sine of x, minus 0. So I'll clean that up. We have y cosine of x plus lambda. Now the x derivative of w, x derivative of y plus sine of x, is 0 plus cosine of x over y plus sine of x minus lambda y sine of x. We'll set that equal to 0. So that's our first equation. Here's our second equation, is the y derivative. So we have 1 times sine of x plus lambda times w sub y over w plus lambda times 1 times cos of x minus 0. And then I'll clean this up. We have sine of x plus lambda times the y derivative of what's inside the log function, so 1 plus 0, divided by what's inside the log function, y plus sine of x, plus lambda times cosine of x is equal to 0. So that's our second formula. And our third equation that we can get for free, f sub lambda, is always just the constraint. So our ln of y plus the sine of x plus y times the cosine of x minus 1 equals 0. So that's our third equation. Because that's our third equation. So our system is 1, 2, and 3. those three equations are the system of equations that we need to solve in order to find the critical numbers of the Lagrange function. And good luck. I wouldn't want to have to finish this problem from beginning to end. We'll stop here.